The trajectory of 20th century aerospace engineering is fundamentally a chronicle of the management of extreme forces. While the public imagination is often captured by the aesthetics of airframe design or the raw power of propulsion, the operational viability of flight relies on the sophisticated management of energy transfer during the most critical phases of operation. Sir George Herbert Doughty, 1901 to 1975, emerged as the preeminent architect of these essential systems, transitioning the industry from primitive mechanical solutions to high-pressure hydraulic and fuel delivery architectures. His career, spanning the infancy of the Royal Air Force to the dawn of supersonic transport, represents a continuous pursuit of mechanical reliability through the innovative application of fluid dynamics and material science. George Herbert Doughty was born on April 27, 1901 in Pershore, Worcestershire, into a family where the intersection of chemistry and commerce was a daily reality. His father, William Doughty, was a local chemist, providing an early exposure to scientific principles. However, Doughty's path was redirected by a pivotal traumatic event at the age of 12. In 1913, while conducting experiments with photographic materials, specifically magnesium powder, an explosion occurred that resulted in the permanent loss of his right eye. This physical setback, rather than discouraging his technical ambitions, seemingly catalyzed a lifetime of meticulous attention to mechanical detail and a resilient approach to engineering challenges. The onset of the First World War further disrupted his formal education at the Worcester Royal Grammar School. At 14, Doughty was required to leave school to support the various family businesses, as his older brothers had been conscripted for military service. This early entry into the workforce provided a practical foundation in business operations that would later define his industrial empire. His formal engineering journey began with an apprenticeship at Heenan and Froude in Worcester, a company then engaged in the manufacture of aero engines. This exposure was followed by a series of draftsman roles that allowed Doughty to observe the rapid, often chaotic evolution of aircraft design in the post-war period. By July 1918, Doughty had relocated to London to join the British Aerial Transport Company, BAT. Under the guidance of prominent designers such as Robert Norden and Frederick Koolhoven, he was immersed in a high-pressure design environment that accelerated his professional development. His subsequent tenure at A.V. Rowe & Company at Hamble proved even more significant. By the age of 22, Doughty had successfully designed the landing gear for the first Cierva Autogiro and the Avro Aldershot. These early successes underscored a nascent realization: the undercarriage was not merely a structural support, but a complex energy management system. The transition from early biplanes to high-performance monoplanes and eventually jet aircraft required a fundamental shift in how power was distributed throughout the airframe. In the 1920s, landing gear were often fixed and rudimentary, utilizing rubber compression or simple steel springs to absorb landing loads. As aircraft weights increased and the need for aerodynamic streamlining led to the development of retractable undercarriages, traditional mechanical linkages became prohibitively heavy and complex. George Doughty's primary contribution during this era was the realization that high-pressure hydraulics offered a superior power-to-weight ratio for these functions. Central to Doughty's mastery of hydraulic systems was the development and refinement of the Vardell pump. This unit represents a departure from standard pump designs of the era, which often suffered from significant energy loss and heat generation when the system was not under active load. The Vardell pump leverages a sophisticated dual-stage architecture to maximize energy transfer efficiency. The first stage of the Vardell pump consisted of a low-pressure external gear pump, which provided a consistent priming flow. The second, high-pressure stage, utilized a radial configuration of 7 pistons. The mechanical brilliance of the Vardell pump lay in its control mechanism. The displacement was not controlled by traditional swash plate angling, but rather by acting on a variable hydraulic resistance that limited the intake to the high-pressure pump. When system demand was low, this resistance would effectively slow the motion of the pistons during their intake stroke. Consequently, the pistons would temporarily lose contact with the rotary cam, limiting their effective stroke and reducing the power required to drive the pump. This limitation of the effective pumping stroke provided a self-regulating mechanism that ensured high pressure was available instantly without the parasitic drag of a constant displacement pump. In the context of energy transfer reliability, this meant that the hydraulic system could maintain its readiness throughout long flights with minimal wear on the internal components, a critical factor for the emerging long-range bombers and transport aircraft of the 1940s and 1950s. As the aviation industry entered the jet age, the requirements for fuel delivery shifted from the relatively low-pressure needs of carbureted piston engines to the high-volume, high-pressure requirements of gas turbines. Doughty Equipment Limited, and later Doughty Fuel Systems, became instrumental in solving the unique combustion challenges posed by these new engines. A primary challenge in early gas turbine operation was maintaining stable combustion across a vast range of altitudes and engine speeds. Conventional fuel nozzles often fail to provide adequate atomization at low fuel flows or high altitudes, leading to flameouts, a catastrophic failure of energy transfer reliability. Doughty's response was the development of the spill burner. The spill burner mechanism maintained a high constant supply to the burner at all times, ensuring vigorous fuel swirling and atomization within the burner chamber. The actual volume of fuel injected into the combustion chamber was controlled by a valve in a spill line that allowed excess fuel to be returned to the pump inlet. This meant that even when the engine was idling at high altitude, the fuel atomization remained optimal because the internal pressure of the burner did not drop. This innovation was critical for the operational success of engines like the de Havilland Ghost and the early Rolls-Royce turbines that powered the first generation of British jet fighters and airliners. Energy transfer reliability in the context of aircraft landing gear refers to the consistent ability of the system to convert the kinetic energy of a descending aircraft into a manageable form, usually thermal energy, without compromising the airframe's structural integrity. Doughty's work in this field evolved from the mechanical refinement of existing shock absorbers to the invention of entirely new classes of resilient devices. Before Doughty's refinements, the Oleo strut, an air-oil hydraulic shock absorber, was already in use, but its performance was often inconsistent. The basic principle involves a cylinder filled with gas, nitrogen, and oil. The gas acts as a spring, supporting the weight of the aircraft, while the oil acts as a damper, forced through an orifice to dissipate the energy of impact. Doughty focused on the precision of the energy dissipation. He refined the use of tapered metering rods within the orifice. As the strut compressed during landing, the rod would move through the orifice, gradually changing its effective area. This allowed for a programmed resistance, soft at the initial touchdown to prevent a harsh jolt to the airframe, and increasingly firm as the stroke reached its limit to prevent bottoming out. This precise control of energy transfer was vital as aircraft grew from the 5,000-pound fighters of the 1930s to the 30-ton bombers of the 1940s, such as the Lancaster and Holocaust. Perhaps the most radical of Doughty's inventions was the liquid spring. Conventional engineering wisdom held that liquids were incompressible. Doughty challenged this by demonstrating that at extremely high pressures, approaching 50,000 pounds per square inch, certain hydraulic fluids exhibited significant compressibility. The Doughty liquid spring utilized this property to create a combined spring and shock absorber in a single incredibly compact unit. A piston was forced into a chamber completely filled with fluid. Because the fluid could compress, the entire volume of the liquid acted as the spring. This eliminated the need for a separate gas chamber, drastically reducing the size and weight of the suspension unit. However, the reliability of a 50,000 psi system was entirely dependent on the integrity of the seals. Doughty's engineers developed specialized non-elastic high-pressure glands and researched polymorphic materials that could withstand these extreme pressures without leaking.
The liquid spring offered a weight and space efficiency advantage of up to 300% over traditional oleopneumatic systems, making it the preferred choice for high-performance applications where space within the wing or fuselage was at a premium. The true measure of Doughty's reliability concepts was found in the mass production requirements of the Second World War. A design that is reliable in a laboratory is of no use if it cannot be manufactured in the thousands with consistent quality. George Doughty's Aircraft Components Company, renamed Doughty Equipment Limited in 1940, became the primary supplier of hydraulic and undercarriage systems for the Allied war effort in Europe. The scale of production achieved between 1939 and 1945 was unprecedented. Doughty's plants produced 87,782 landing gear units and nearly 1 million hydraulic components. This production was not limited to a single aircraft type, but spanned 28 different models, including the Hawker Hurricane, Typhoon, Avro Lancaster, and the Short Stirling. The reliability of these systems was such that they became the standard by which Allied performance was measured.